Welcome back to the deep dive. Today, we are taking a fascinating look at the earliest years of the space age, but not from the perspective you might be used to.
That's right. We're not just looking at historical events, we're looking through the eyes of a scientist, Joseph Shklovsky, who was writing about this cosmic revolution as it was actually happening.
And the source material we're drawing from is his classic work, Universe, Life, Reason.
Exactly. And what makes it so compelling, so immediate, is that he was documenting this astonishing transformation that, began literally on humanity's watch. We're talking about the 30-year period right after Sputnik.
And he frames it in this really powerful way. He calls it the irresistible expansion of human reason.
It's a great thesis, isn't it? Because it captures the scale of it. This wasn't just a few scientific advances here and there. It was a fundamental shift in our role in the cosmos.
A complete paradigm shift. I mean, in just a few decades, space exploration went from being abstract theory, something in science fiction, to a full-blown industrial reality.
And our mission for this deep dive is to unpack the pace and, I guess, the structure of that revolution. We're going to track three distinct phases of expansion, just as they're laid out in the source material.
Okay, so what's the first phase?
We begin with the practical, almost utilitarian integration of near-Earth space. Then we'll move to the moon.
The moon is this essential foundation, the first great scientific platform.
Precisely. And from there, we examine the really pioneering voyages, the ones that pushed our technology, our artifacts to the planets and, critically, outside the solar system entirely.
And as we go, we'll discover the real philosophical core of his argument. This idea that for the first time in 4.5 billion years, human creations began to fundamentally alter, even in a small way, the general plan of the solar system.
It's a profound thought.
It really is. Okay, let's start there with that initial phase. When the first satellites went up, the world saw it as this huge symbolic victory, right? A geopolitical race.
Of course. That's how most people experienced it.
But the sources we're looking at highlight that the success was immediately, and I mean immediately, channeled into something far more pragmatic.
Yes, the rapid rise of a massive specialized space industry complex. I think the speed of that transition is what's truly staggering. And
Yeah.
It's easy to forget.
So it wasn't just about planting flags.
Not at all. Within those first few decades, near-Earth orbit stopped being a demonstration arena. It became a functioning utility belt for Earth.
A cosmic utility belt. I like that.
It was swiftly and, very robustly integrated into daily human practice. And that, right there, is the clear sign that the expansion of reason was, in its first stage, fundamentally utilitarian.
So let's talk about the most immediate and revolutionary impact. That has to be communications, right?
Absolutely. The source specifically highlights systems like the Molniya satellites.
Explain what these were. What was the problem they were designed to solve?
Well, the Molniya system was an engineering marvel, really, designed to solve a colossal geographic problem. If you have a country with a vast landmass, think about the Soviet Union or Canada, providing reliable terrestrial relays for TV broadcasts and other communications is incredibly difficult and prohibitively expensive. You need thousands of towers.
So space becomes the shortcut.
It's the ultimate shortcut. By placing these satellites in these very particular, highly elliptical orbits, the Molniya orbit, as it's known, they could essentially hang in the sky over a huge area for a long period.
Ah, so it's not a simple circular orbit.
No, not at all. It's a very clever solution. This long hang time allowed them to relay television broadcasts and other communications across thousands of kilometers, connecting these massive remote territories.
So people living in, say, the far east of the country could suddenly get central television programming consistently.
For the first time ever. You can't overstate the impact of that. It's not just an infrastructure project. That's a sociocultural link created almost instantaneously by this new cosmic technology. It shrinks the world.
It really does. But the source has this wonderfully dry, almost funny observation about it.
It's fantastic. While he's praising this cutting-edge cosmic technology, this incredible feat of engineering, he notes that it was, and I'm paraphrasing here, somewhat regrettable that the artistic quality of the programming sometimes lagged behind the sophistication of the delivery system itself.
That is a classic scientific understatement. It's perfect. The scientists have solved a problem of physics, moving a signal across the planet only to observe that the content is still, well...
Still terrestrial.
Yes. That contrast between the cosmic ambition and the human banality of it all is just hilarious.
It's a great reminder, though, even the greatest technological leaps are still fundamentally in service of everyday human activities. But, beyond entertainment, The utility quickly moved into absolutely critical global systems.
Particularly meteorology.
Exactly.
The text describes the introduction of these continuously patrolling meteorological satellites as putting global meteorology on a firm experimental basis. What does that actually mean? What's the conceptual change there?
It's a colossal leap. It's the difference between observation and prediction, or at least reliable prediction. For all of human history, large-scale atmospheric dynamics, typhoons, cyclones, massive cold fronts were considered these vast, uncontrollable, almost capricious forces of nature.
The gods throwing lightning bolts?
Pretty much. I mean, an astronomer could look at the stars and predict their movements to the second, centuries in advance. But the storm brewing just off the coast, that was unpredictable chaos.
And satellites ended that chaos.
They did. For the first time, this continuous global patrol by satellites provided the constant stream of data needed to track, model, and predict these huge atmospheric perturbations in incredible detail,
So the Weather Service could suddenly operate on a truly global scale.
fundamentally changing the risk management landscape. For coastal communities, for agriculture, for shipping routes, it shifted meteorology from being a largely descriptive science to a predictive experimental one. It became a hard science.
And the practicality didn't just stop at saving lives, which is obviously huge. It extended directly into national economic forecasting. That seems like a surprisingly unglamorous but incredibly vital application.
This is where you see space tech getting integrated really deeply into resource management. We are talking about detailed forecasting of harvests over immense geographic areas.
I can't even imagine trying to do that from the ground.
Well, think about it. How would you gather real-time data on crop health across millions of hectares with just ground personnel? It's impossible. Satellites solved that problem, and that data is absolutely critical for planning logistics, for resource allocation, for predicting commodity markets.
And it wasn't just for broad-scale agriculture. The utility got very specific, didn't it? It targeted specific threats.
Yes. For example, identifying pest infestations in really difficult-to-reach areas like the remote taiga regions.
Places where an outbreak could spread completely unchecked before anyone on the ground even knew it was happening.
Precisely. Satellite imagery, often using specialized infrared bands, allows for incredibly rapid identification and therefore intervention. It's a powerful tool.
And it even helped with something as localized as fishing.
Immensely. Satellites could draw sea surface temperatures, plankton density, ocean currents, all the things that tell you where the fish are likely to be. That allows for much more efficient, targeted fishing operations. It saves an enormous amount of time and fuel.
So the core takeaway from this first section is really clear. The initial expansion into space was immediate, it was industrial, and it was profoundly useful.
Exactly. The success of that utilitarian phase established the industrial and operational baseline. It proved that access to the cosmic environment wasn't a luxury or a vanity project. It was a highly valuable asset that could be integrated directly into our global infrastructure.
And that successful prototype of cosmic industry is what laid the groundwork for the next, much riskier phase.
The phase of pure exploration.
Right. And that successful foundation in near-Earth orbit is what paved the way for the first great exploratory target, the Moon. The source describes it as the target of a full-scale attack by researchers.
Attack is a strong word, but it captures the intensity of the effort. And that attack began, of course, with automation. The very first big success was a Soviet achievement of the first soft landing of an automated station.
And the images it sent back.
They were unforgettable. Just a quiet, dusty lunar surface scattered with stones. It was the first time we'd seen it up close like that, and it really signaled that we had moved past just doing simple flybys. We were there.
But the psychological high point, the moment that's really etched into our collective memory, remains the manned mission.
Of course. The American landing of Armstrong and Aldrin, July 1969, and then the subsequent Apollo cruise.
The scale of that achievement is still, it's hard to wrap your head around, even today.
It really is. And Armstrong's famous quote, "That's one small step for a man, one giant leap for mankind," it perfectly captures the philosophical meaning of that moment. It was the physical realization of this irresistible expansion of reason beyond our home world.
And the sources remind us that technologically, it was a miracle of modern technology. We tend to just remember the picture of the footprint, but we often forget the sheer number of steps involved beyond the actual landing.
You're so right. I mean, think about the complexity. First, you have multi-hour work being performed in a completely hostile vacuum. Then you're setting up specialized scientific equipment, like seismic stations.
All while wearing a bulky, pressurized suit.
Exactly. Then you have to collect pristine geological samples. Then comes the critical part, the lunar ascent, launching off the moon and performing a perfect orbital rendezvous with the command module that's orbiting high above.
And any one of those steps, if it failed.
It would have meant catastrophe. And then you still have the final stage, the safe return, re-entry,
Yeah.
and splashing down precisely at the pre-calculated target coordinates on Earth. It was an astonishing chain of successes.
Which leads us directly to the inherent risks. I mean, space exploration, especially in those early days, was absolutely not a tourist stroll.
No, absolutely not. The sources make a real point of injecting a sense of genuine peril into the narrative, and they use the perfect anecdote to illustrate it. Apollo 13.
The ultimate successful failure.
Exactly. The crew suffered a catastrophic accident hundreds of thousands of kilometers from Earth. It should have been a death sentence. Yet, through extraordinary skill and ingenuity, both from the astronauts and the mission control crews on the ground, they returned safely, literally on one wing, as the source vividly describes it.
That moment must have felt terrifyingly similar to the earliest days of global exploration on Earth.
It was. The text explicitly draws that parallel, comparing the risks in space to the perils faced during the era of the great geographical discoveries. That era also came with a considerable human cost.
So the implication is that we have to accept that danger is just an inevitable part of pioneering endeavors like this.
We do. The goal isn't the impossible task of eliminating risk entirely. It's the diligent, relentless work of minimizing those inevitable dangers through better technology and exhaustive preparation.
Now, while the U.S. was focused on this immense effort and risk of manned exploration, the Soviet contribution continued to refine the art of long-duration automation.
Yes, the Lunokhod mobile vehicles. They were the proof of concept for a sustained robotic presence. Lunokhod 1 operated for 10.5 lunar days.
And a lunar day is much longer than an Earth day.
Right, and more importantly, a lunar night is 2 weeks of absolute bitter cold. So what that operational time means is that it survived multiple extended lunar nights where the temperatures just plunged to a brutal minus 150 degrees Celsius.
The engineering to keep the electronics from freezing solid is incredible.
It's exceptional. To maintain power, thermal control, and system integrity over those temperature extremes, all while driving over 10 kilometers of complex rocky terrain. It was a masterpiece of robotics.
And Lunokhod 2 pushed that even further.
It did. It covered 37 kilometers in just 5 lunar days. And on top of that, other Soviet automated capsules successfully drilled into the lunar soil and returned those samples to Earth.
So there's a really interesting contrast there. If the American missions proved humans could visit the moon,
The Soviet automated efforts proved that robots could stay and work for long periods. They provided that crucial scientific longevity.
and this idea of longevity naturally leads to the long-term vision that's laid out in the text for the 1980s, the idea of transforming the moon into a permanently operating scientific platform.
That was the next logical step. The goal was to establish a fully autonomous observatory. It would operate largely on its own, gathering massive amounts of scientific data, but it wouldn't be completely isolated.
How so?
It would be periodically visited by astronaut scientists. Their job wouldn't be to run the experiments day to day, but to perform a purely logistical task. Retrieve the accumulated scientific materials, things like photographic films that you can't easily transmit, while the station continuously sent real-time data back to Earth telemetrically.
So it becomes a kind of cosmic research station, a relay point. The advantages for certain fields of astronomy must be immense, just given the lack of atmosphere.
They are phenomenal. And the astronomical community had recognized this almost a century earlier. It's great. The source includes this reference to the 19th century American astronomer Simon Newcomb.
What did he say?
He jokingly remarked that the souls of true astronomers should go to the moon after they die, because the conditions there are truly ideal for observation. No atmosphere, no clouds, no light pollution.
That's a deep-cut astronomical burn. I love it. But in practical terms, which specific types of observation benefit the most from being in that vacuum?
Well, while some radio observations might actually be better served by space satellites with variable orbits, and we'll get to that in a minute, the moon is considered an extremely convenient platform for 2 key areas. First, X-ray astronomy.
Because Earth's atmosphere just blocks all of that.
It completely blocks high-energy radiation like X-rays, so ground observation is impossible.
Yeah.
From the moon, the entire X-ray universe becomes visible.
And the second area.
The second is selenophysical observations. That just means studying the moon itself, its seismic activity, its history of meteoric impacts, and monitoring the corpuscular radiation, the solar wind, that constantly streams from the sun. Establishing a base there was all about exploiting these specific unique advantages.
So the moon provided a solid platform, a stable place to observe from. But to look at the truly distant and highly detailed features of the universe, we need to talk about geometry.
Yes, specifically the geometry of observation. This is where the concept of very long baseline interferometry, or VLBI, comes into play.
And this is a crucial area expansion because it represents the moment human reason sought to overcome the fundamental limits imposed by the size of our own planet.
That's the perfect way to frame it. The ability of any telescope to resolve fine detail, to see small things far away, is expressed by a simple formula. Phi equals lambda over d.
Okay, break that down for us.
The angular resolution, that's phi, is equal to the wavelength of the radiation you're observing, lambda, divided by the distance between your observation points. That distance, d, is what we call the baseline.
So to improve your resolution, to see smaller details, you either need to use shorter wavelengths, which isn't always an option,
Or you need a significantly larger baseline, a bigger d.
and on Earth, we did that by linking telescopes across continents.
Exactly. By placing radio antennas thousands of kilometers apart, creating intercontinental baselines, ground-based radio astronomy achieved resolutions of about 10 to the minus 3 arcseconds.
Just to give us some context, how does that compare to, say, the Hubble Space Telescope invisible light?
It's orders of magnitude better. An optical telescope, even a great one, might struggle to get down to 1 full arcsecond. So this was a 1,000-fold improvement in sharpness. It was absolutely revolutionary.
And what did that hyper-resolution suddenly allow us to see?
It was crucial for studying extremely compact, distant, and energetic objects. For instance, it gave us key information on what are called cosmic masers.
Remind us what those are.
Sure. They're basically clouds of gas in space that act as natural, incredibly intense amplifiers of radio waves. Being able to pinpoint the exact location and shape of these masers allowed us to map star-forming regions with incredible precision and observe the dynamics right near supermassive black holes.
But even with antennas spread from Europe to North America, you eventually run into a hard physical limit.
You do. You run into the same problem. Earth has a finite diameter. You simply cannot make the baseline larger than about 12,000 kilometers. The planet just isn't big enough.
The constraint is absolute.
It is. And so the solution, the next logical step, had to be the cosmic baseline. This is the project to move one of the antennas into space.
And the concept is really elegant, isn't it?
It is. One massive antenna remains anchored on Earth, providing the huge collecting area, the receiving power, and then a smaller, highly mobile receiver is placed on a satellite in a very, very elongated orbit.
That sounds like an orbital mechanics nightmare just to keep track of the 2 points and synchronize the data. What's the overwhelming advantage that justifies all that complexity?
The advantage is all geometrical. First, the baseline distance becomes astronomical. It could span hundreds of thousands of kilometers, which dramatically increases your resolution, pushing it down to 10 to the minus 4 or even 10 to the minus 5 arcseconds. But second, and this is a really critical nuance,
Go on.
the baseline is not only large, it's variable.
Why is the variability so important? Why not just park the satellite way out there and keep the baseline fixed?
Because if the baseline is fixed, you only get one narrow slice of information about the source's structure. It's like looking at something through a very thin slit. But as the satellite moves in its elongated orbit, the separation distance and the orientation of the line connecting the two antennas are constantly changing.
Ah, so you're seeing it from all these different angles.
Precisely. By collecting data across all of those varied orientations and distances, you gather enough information to mathematically reconstruct not just the angular size of the source, but its actual two-dimensional shape. You are essentially creating a synthetic, planet-sized eye that can map the morphology of distant, compact radio sources.
And this wasn't just a theory on a blackboard. The source details early, successful implementations of this.
Yes, this was all about demonstrating feasibility. In 1979, they successfully installed and tested the KRT-10, a 10-meter diameter cosmic radio telescope, on the piloted Salyut orbital station.
Which proved that these complex, large astronomical instruments could actually operate effectively on a manned space platform.
Exactly. And the next logical step from there was to push that baseline out almost to the orbit of the moon itself.
To maximize that value.
That was the goal. The source mentions the ambition to move an antenna nearly to the lunar orbit to get the longest possible baseline. And this led to major international collaborations like the Radio Astron satellite project.
That involved numerous nations, right?
Yes, Russia, India, Finland, the USA, many others. This satellite, with its 10-meter antenna, was slated for a high elliptical orbit with the singular aim of creating baselines spanning hundreds of thousands of kilometers.
And this is where this very technical discussion about interferometry connects directly back to the philosophical core of Shklovsky's work.
It absolutely does. Because this massive increase in resolution, this profound new ability to focus on and isolate incredibly faint, distant radio signals over massive distances, has serious future significance for the central problem that this entire work addresses: the detection of distant civilizations and the establishment of contact, SETI. The engineering marvels we develop for pure cosmological science are, at the same time, the most potent tools we possess to listen for our neighbors.
So if the moon was the first great leap, the next phase was the true outward journey, the exploration of the solar system's inner and outer reaches.
Venus, Mars, Jupiter, Saturn, Uranus, all pioneered by this fleet of incredibly sophisticated automated Soviet and American stations.
And this stage represents a huge expansion of human artifacts into the cosmos. We move from just orbiting our own planet or visiting our local satellite to actively sending these creations of human intellect to other planetary bodies.
And that action, according to the source, emphasizes a really deep principle. For the first time in the solar system's 4.5 billion-year history, objects move from one planet to another.
The source has that great line saying these sophisticated creations change the general plan of the solar system. Now, wait a minute. We're talking about tiny metal probes. They're pinpricks in the vastness of space. How does that really change the general plan? Is that just symbolic, or is it something more?
I think it's both. You're absolutely right. The change is minimal in terms of mass or gravity. It's negligible. But conceptually, it's profound. For billions of years, the general plan of the solar system was a natural one.
Gravity dictated the orbits, material stayed where it formed?
Exactly. But now, humanity has become a non-natural gravitational influence, a source of material transfer. Sending an artifact from Earth to Jupiter, for instance, breaks that purely natural cycle.
It's the very first, tiniest step toward planetary engineering.
That's a great way to put it. It's the crucial conceptual start. It's the beginning of humanity gaining the capacity to manipulate the planetary arrangement, even if future steps like terraforming or active gravitational adjustments are centuries away.
Let's talk about the immense technical difficulties those pioneers faced, starting with Venus. The Soviet landers had a brutal time.
Venus is the epitome of an environmentally hostile planet. It's a hellscape. The Soviet landers faced enormous atmospheric pressure, like being a kilometer deep in the ocean, and surface temperatures hot enough to melt lead.
So the landers just couldn't last long.
Mere minutes, in some cases. But in those incredibly brief operational windows before they were crushed and cooked, they provided invaluable first-hand data.
Our first ground truth.
Our first ground truth. They measured the atmospheric temperature, the pressure, the chemical composition, the cloud structure, and even gave us our first photos from the surface. And they confirmed that our prior models were often overly optimistic. The brevity of their lifespan just highlights how unbelievably intense those conditions are.
And that's a sharp contrast with the activity we saw on Mars. Mars offered persistence.
Mars proved to be a far more welcoming environment, if still very challenging, for long-term robotics. The American Viking 1 and Viking 2 landers demonstrated sustained activity on the surface.
They weren't just alive for minutes.
They transmitted detailed images, conducted complex chemical experiments looking for signs of life, and provided meteorological data from the Martian surface for several years. It was a massive demonstration that Mars was a viable place for long-term robotic platforms. A huge leap beyond the few minutes of life we got on Venus.
And it's so important to remember how utterly incomplete our understanding of Mars was before these missions began.
It's easy to forget, isn't it? Before the space era, the best astronomical photographs from Earth couldn't resolve surface details smaller than several hundred kilometers. Our knowledge was based on these vague, blurry notions of canals and generalized topography.
And the Mariner 4 mission just shattered all of that.
It did. It was the first probe to give us a decisive close-up look at the surface, and it confirmed the presence of numerous craters. It showed that Mars, like the Moon, had endured a history of heavy bombardment. This data was essential. It forced us to rewrite the geological history of the entire solar system.
So after getting a handle on Mars itself, Mariner 9's mission in 1971 took on an even harder task, one that had been proposed nearly a decade earlier.
Yes, accurately photographing the two tiny, dark, and fast-moving moons, Phobos and Deimos, from Mars' orbit.
And that was an astonishing targeting challenge.
Oh, absolutely. These moons are just small, dark rocks with very low reflectivity, and they're zipping around the planet. So the automatic station first had to achieve a stable orbit around this massive planet, and then its targeting systems had to function flawlessly to aim the camera precisely at these tiny pinpricks of rock in the Martian night. It was a true stress test for automated intelligence.
And what Mariner 9 revealed about Phobos was dramatic.
It was startling. Phobos was revealed to be this massive, stony block, sort of oval-shaped, with its largest dimension reaching 21 kilometers. And its surface was utterly ravaged, just completely riddled with craters, suggesting a history of constant violent collision, likely with asteroids from the main belt.
And there's one specific feature that suggests a truly catastrophic event in its past, right? A major missing piece.
Yes, the source notes that the upper left edge of Phobos appears visibly damaged. It looks like a huge chunk is missing, suggesting that a significant piece of the moon actually broke off in the distant past following an incredibly powerful collision.
Wow.
And in fact, another photo confirmed this violence. It showed a massive crater that's about 7 kilometers in diameter.
So that's roughly 1/3 the size of the entire moon.
Exactly. Can you imagine an impact of that magnitude on a relatively small body? It must have nearly shattered it.
And you can see the evidence of this ancient violence just in the boundary between light and shadow on the surface.
That's right. The terminator line, the boundary separating the illuminated and shadowed parts, is incredibly irregular and jagged. It immediately confirms the deeply ruined, heavily pockmarked nature of the surface. This is a very, very old world.
And what about its smaller companion, Deimos?
Deimos was similarly oval-shaped, about 12 by 13.5 kilometers. Its images also showed clear signs of bombardment, including 2 prominent craters near its terminator, each about 1.5 kilometers across. Still heavily battered.
This new data also forced astronomers to significantly revise the size estimates for both moons, which is interesting in itself.
It is. They turned out to be about 1.5 times larger than previously assumed from telescopic observations. And the reason for the error was simply how dark their surfaces are.
They're not very reflective.
Not at all. Their reflectivity is significantly lower than Mars's. It's much closer to the reflectivity of our own moon. Their ancient carbonaceous surfaces just absorbed so much light that they appeared smaller and fainter from a distance.
And that dark, heavily bombarded geology leads to a pretty strong conclusion about their history.
The sheer density of meteorite traces suggests extreme antiquity. They are very likely pristine, if battered, time capsules dating back to the earliest stages of the solar system's formation, that chaotic period 4.5 billion years ago.
But despite all this incredible new data, there's still a persistent mystery about their orbital mechanics.
And that's the fun of planetary science, isn't it? It is still an unsolved puzzle how their orbits became almost perfectly circular and lie almost exactly in Mars's equatorial plane. Tidal effects for Mars are the prime suspect, but the precise mechanism of that evolution is still an area of very active research.
Now, as we're discussing the orbiting of these 2 natural satellites,
Yeah.
we have to acknowledge that humanity has now added its own artificial ones to the Martian system.
Indeed. Several Earth-made artificial satellites now orbit the red planet. Their small and, relatively short-lived solar and planetary perturbations will eventually cause them to deorbit and crash into Mars. But they represent that continuing pattern of human expansion.
Which prompts the speculation that's detailed in the source material. Will we eventually build automated observatories on Phobos or Deimos?
It's the logical next step.
What would be the specific advantage of using a Martian moon as an observatory platform rather than just being in Mars orbit?
A moon platform offers unique stability and distance from any potential Martian atmospheric interference. Specifically, the source suggests they would be ideal for systematic monitoring of the sun. They provide a stable, relatively cold platform with a clear view of the inner solar system, making them superior to a constantly vibrating, potentially shorter-lived artificial Mars orbiter.
So we've charted this incredible journey from near-Earth utility to the solid platforms of the Moon and Mars's satellites. But the final act of this expansion is the ultimate breakthrough.
The flight of Pioneer 10, humanity's first true breach of the solar system frontier.
This is such a profound leap.
It is. After observing Jupiter, Pioneer 10 received this massive gravitational boost from the giant planet, which propelled it onto a trajectory to leave the solar system forever. It was projected to just wander the immense void of the galaxy for billions of years. It's the ultimate act of cosmic ambition.
What's the estimated longevity of a human artifact like that in the interstellar void? I mean, what happens to it out there?
Well, it's surprisingly robust. The probability of it colliding with a significant body, like another star or a planet, is infinitesimally small. It will, however, face a continuous bombardment by sparse interstellar hydrogen atoms.
A kind of cosmic sandblasting.
A very, very slow one. Over billions of years, this will form a unique scale or patina on its surface, but the underlying structure of the human artifact, specifically the plaque we're about to discuss, will remain largely intact. It's a time capsule designed for geological timescales.
And that knowledge, the knowledge of this incredible duration and the infinitesimal chance of discovery, is what led the designers to include a message.
The famous stainless steel plaque, intended to convey the absolute minimum necessary information about Earth civilization to any highly intelligent alien entities who might, in the very remote future, find this tiny fragment.
And the plaque is one of the most intellectually complex messages ever designed, isn't it? It's entirely coded in what's hoped to be universal physics.
It is. It's a profound statement of faith in mathematics and science as a common language across the cosmos. Let's try to decode the structure because it's just brilliant.
Okay, we have to start with the scale. That's the foundation of the entire message.
That's component number one. The plaque features two small concentric circles at the top. These represent a proton and an electron. The horizontal line between them symbolizes the spin-flip transition of a neutral hydrogen atom.
The famous 21-centimeter hydrogen line.
The very same. It produces a radio signal at a frequency of 1420 megahertz.
And why hydrogen? Why is that the key?
Because hydrogen is the most abundant element in the entire universe. Its physics are universal. So by referencing the 21-centimeter line, they establish a universal natural unit of length and time for the entire plaque.
So then, by comparing this universal unit to the realistic figures of the human male and female on the plaque?
The recipients can deduce human height. The man is shown to be about 180 centimeters, the woman 164, and the figures themselves are drawn realistically without clothing to convey our basic biological form.
Okay, so they know who we are and how big we are. Next, the plaque tells them where we launched from.
That's component two. The solar system map at the bottom. It's a simple schematic showing the sun and the 9 planets in order of distance.
And crucially, the distances are noted on the map.
Yes, above and below the planets, expressed using the binary system, with that 21-centimeter wavelength as the fundamental unit of distance. And there's an added trajectory line. It runs from the 3rd planet Earth out to the 6th planet Jupiter, where Pioneer 10 got its gravity assist. And the line ends with an arrow, showing the trajectory out of the system and a little schematic of the probe itself.
That is a sophisticated roadmap. But the most challenging element of the plaque, the most baffling part, is component 3.
Establishing our position in the galaxy, and most amazingly, the exact launch time.
How on earth do you do that?
This is handled by that complex star-shaped figure on the left. It uses pulsars as galactic landmarks. Pulsars are these highly precise cosmic clocks, these rapidly spinning neutron stars that radiate intense, regular radio pulses.
So each of those rays in the starburst pattern points to a different pulsar.
Exactly. Each ray points from our sun to a known pulsar. The length of the ray is proportional to the distance between the sun and that specific pulsar. So if the aliens know where those pulsars are, they can triangulate our location.
But that's the location. How do they get the launch time?
This is the genius and, in a way, the heartbreak of the plaque. The periods of those respective pulsars, how quickly they're spinning, are given on each ray segment, again, using the 21-centimeter hydrogen frequency as the natural unit of time. And there's a single longest horizontal ray that indicates the distance from our sun to the center of the Milky Way galaxy, giving a fixed reference point.
So the message is complete, it's sophisticated, it's all coded in universal physics. But the challenge for the extraterrestrial recipients, especially when you factor in billions of years of travel time, seems almost insurmountable.
It's a phenomenal problem in what you could call cosmic archaeology. Pioneer 10 is only traveling at about 10 to 20 kilometers per second relative to the nearest stars.
Which sounds fast to us, but on a galactic scale is a crawl.
It is. It will take hundreds of thousands of years just to get into the vicinity of another star system. Over millions or tens of millions of years, the likely time frame for discovery, if it ever happens. The periods of those pulsars change significantly. They're all constantly, but predictably, slowing down, and they all do so at different rates.
So the map becomes outdated and the clock loses time.
Precisely. And their positions relative to the sun also shift slightly over cosmic time. The aliens would need to be, as the source puts it, very clever They'd need to know the changing periods of all the pulsars in the galaxy, which number more than 100,000, and then perform a complex, backward extrapolation over millions of years to pinpoint exactly when and where the launch occurred.
So they aren't just reading a clock, they have to reconstruct a complex, dynamically changing astronomical history.
They do. It's an incredible intellectual challenge.
It's a beautiful thought, but it really does end on a somber reflection, just given the sheer scale of time involved.
It forces us to confront our own mortality as a civilization. The final reflection offered by the source is that billions of years from now, when this plaque might finally be studied by some intelligent life form, Earth civilization may very well no longer exist. Cosmic archaeology is a science that has to accept that its subject may be long gone by the time it is ever studied.
This deep dive has spanned light years and billions of years. We've moved from the launch of Sputnik and the very practical conquest of near-Earth orbit to the engineering resilience of the lunopods on the moon.
The high-resolution power of VLBI, and now this ultimate philosophical act of sending Pioneer 10, a deeply coded message, a cosmic postcard out into the void.
The overarching theme, this irresistible expansion of human reason, it seems to manifest in two ways.
I think so. There's the physical expansion through our artifacts, and then there's this intellectual expansion through our ability to create a universal language coded in fundamental physics.
Yet all of these incredible achievements seem to reveal a deep paradox within the source material itself.
Yes, the paradox being the probability of contact.
What do you mean?
Well, while we dedicate this immense intellect to creating this complex stainless steel plaque designed to survive for eons and be deciphered by genius aliens, the source makes a fascinating statistical assertion.
That it's probably not how they'll find us.
Exactly. It says it is incomparably more probable for an alien civilization, if one exists, to simply land on Earth, given the vastness of the universe and the time available, than it is for them to ever locate that infinitesimally small drifting fragment that is Pioneer 10.
So we spend all that effort coding a message for a distant future, when the most likely scenario is just a knock on our front door. That's a classic example of cosmic ambition running headlong into statistical reality.
And that reality is shaped by the very technology we discussed earlier today.
Yeah.
We spent a lot of time detailing very long baseline interferometry, VLBI, and its ability to achieve that unprecedented angular resolution.
Right. Which makes it a critical tool for studying quasars and for SETI.
And for SETI efforts. It gives us the targeting precision we need to conquer interstellar distance, not just physically, but intellectually, by listening with incredible focus. The same tools that map cosmic masers could potentially isolate a single artificial signal from a distant star.
So here is the provocative thought we'll leave you with. This entire discussion has focused on the physical conquest, the rockets, the landings, the probes moving through space.
But given that a technology like VLBI is the key technological bridge to the search for intelligence, how might the very nature of that conquest shift?
Is the true measure of our reason not the ability to send a tiny probe out for billions of years,
But the ability to develop the sensitivity and resolution necessary to conquer the interstellar silence and finally confirm that we are not alone? What happens when our telescopes, designed to see the universe, finally hear our neighbors? That, right there, is the next chapter of cosmic expansion.